We did the distillation project, and basically in separation, you have a lot of energy that's required in the U.S. The energy consumption that's required for distillation columns is 6%. So we're looking at how we can reduce the energy toll that I guess we take overall. So that's our distillation column. On the top, we're trying to maintain a distillate composition of 0.95 and over 0.95, and in the bottoms below 0.05. But if it's below 0.95, we're wasting energy because we're not getting to the set point, and over 0.95, we don't need it any more pure, so we're also wasting energy. So we have two variables that we're trying to control, the top and bottom composition, and two variables that we're manipulating, which is the fraction of the feed that's coming in, flow, and the reflux ratio. So when you have multiple control variables and multiple manipulated variables, sometimes it can be hard to know which ones to pair. So we did a relative gain analysis, which looked at the values of the Ks and calculated values based on those relationships, and we found that the main diagonal, where we'd pair the top composition and the reflux ratio, and use the F bottoms to control the bottom composition.
So this model is representing a transit mole balance on tray 17, and as you can see, the number of the tray was counting from the top to bottom. So with the feed in, the top is rectifying sections and the bottom is going to be stripping sections. And the 5 turn here respectively represent the feed coming in from the top liquid flow rate and bottom vapor flow rate, and also the liquid flow rate going out to the top vapor and then the liquid going in. And one thing worth to notice is because of the constant overflow assumptions, we're able to say all the liquid flow rate and vapor flow rate on the top rectifying sections are constant, and we can use that assumption to apply in each of the tray with this model and determine the compositions. Eventually we can determine the overhead and also the bottom compositions.
Okay. So we're just going to jump to the results. We use the MATLAB structure because it has the energy and material balances built into it to run 4 different types of controllers. So this graph here, just starting out, this blue, we have our set point in the dotted lines that it's trying to control to. The blue line is just a PID controller. You can see that there's pretty poor performance controlling to the set point. The yellow is an interacting PID controller where you try to decouple the two control variables and manipulated variables in the yellow here, and you can see it's better than the PID. The orange is the nonlinear controller, which we ran, and then basically we noticed that in the PID interacting controller, the main fluctuations came when there was a disturbance in the feed mole fraction here in the middle of the graph, and so we added a second feed forward component to our PID interacting controller, which was a static feed forward based on the gains of the disturbance to the feed composition and the top reflux ratio. And so with the interacting and then adding an additional feed forward component for the feed composition, we're able to maintain very, very tight control with very small deviations when there was a change in feed composition. Looking at the bottom, there's a little bit different behavior. Again, the PID was the worst, but in this case, the non-linear controller controlled pretty well. It controlled better than the interacting controller, which is different from the top composition. But still, when we added the feed forward, static feed forward to the interacting controller, it performed better than the nonlinear controller. So the last slide here is just, this shows an integration of the errors over the whole time frame. And so you can see that there's really no comparison for controlling top composition with the PID controllers and feed forward. But on the bottom, the nonlinear controller was somewhat comparable, but it would still be out by adding both those feed forward terms. So our recommendation to the distillation unit is to implement a PID controller with 2 static feed forwards, one for the other controlled variable and one for the feed composition. Lastly, we just show you this because we spent maybe, 20 hours in Simulink trying to model the system. But yeah, we realized that we make the assumption that both the process transfer functions and the disturbance transfer functions are first order. And so it's somewhat self-defeating because you're not actually modeling the real system based on the energy and the material in the real system. We're using our approximation to also judge the effectiveness of our controller. So it's not that you don't learn a lot when you model it in Simulink like this. So even though we spent a lot of time, we didn't get a lot of gain from it. And then lastly, this just shows our code in MATLAB that we added our 2 feed-forward controller components. So here's the static feed-forward coefficient times the F-bot, and this is for the reflux ratio. And then we have another static feed-forward coefficient, and then the deviation from the nominal feed condition. And so that seemed to give the best control.